Let's consider the special case of circular orbits. All circles are ellipses, and circular orbits represent a special case for which it is easy to show that Kepler's third law holds true. Also, circular orbits provide an opportunity to introduce some concepts that will be useful later. Let's now go ahead and consider three vectors that are relevant to our discussion. First of all, we have the displacement vector extending from the sun to the planet, in which we will label d. And we also have an acceleration vector due to the gravitational force of the sun pointing in a direction directly opposite of d. And we commonly refer to the acceleration vector as dv over dt to remind us that we're talking about the instantaneous change in velocity. And at this point, we should note that the absolute value of d is constant by definition of a circle in the case of circular orbits, and the absolute value of dv dt is constant because we have accepted Newton's law of gravitation as a premise for our discussion, and that of course equals gm over the absolute value of d squared. And then the last vector to consider is the velocity vector v. Now you might guess that this vector is also a constant, and you'd be right, but how can we prove that? Well, it turns out that there are two ways to prove that, and so let's go ahead and do that right now. First of all, let's be clear about one thing, and that is, regardless of the shape of the orbital path, the velocity vector has to be at all times tangent to that path, because otherwise it would make no sense. So for example, if the velocity vector was in this direction, but the planet actually moved in a different direction, that immediately contradicts the whole concept of a velocity vector. So a velocity vector will always be tangent to the orbital path as long as we assume at minimum that the orbital path is in fact a smooth curve. Now if we go back to our circular orbit and we see the velocity vector here tangent to the circle, we can extend the displacement vector out this way, and when we talk about the angle phi here, we can see that phi is always 90 degrees in the case of a circular orbit because the tangent to a circle is always perpendicular to the radius. Now, for a circular orbit, consider the equation for specific angular momentum. We already proved that h is constant regardless of the shape of the orbit. We just showed that for a circular orbit, phi is always 90 degrees, and therefore sine phi is always equal to 1. So we're left with v equals h over the absolute value of d, and this is constant, so the absolute value of the velocity is also a constant for a circular orbit. There is another way to prove that the velocity is always constant for a circular orbit, and to show that we have to prove that the centripetal acceleration of a planet in a circular orbit is always equal to the velocity squared divided by d.
Centripetal acceleration can be derived by geometrical considerations. Let S equal the path of a planet traveling over a portion of a circular orbit from A to B. If we express theta in radians for now, then theta equals S over D. Let's approximate the distance S with a chord connecting A and B of distance tilde S. For comparison, let's construct a similar triangle from the velocity vectors v1 and v2. Let's place them tail to tail in a vector diagram. The angle between them is also theta, because velocity vectors for a circular orbit are always perpendicular to the corresponding radius. The difference between v1 and v2 is delta v, which I have drawn in here.
Now notice that the green triangle and the blue triangle are both isosceles triangles, and furthermore, their corresponding angles are all equal. So here is angle theta, and the other two angles in all cases equal 180 minus theta divided by 2. So the green triangle and the blue triangle are similar isosceles triangles. Now, because the two triangles are similar, the ratio of one side to another in the case of one triangle is going to equal the ratio of the two corresponding sides of the other triangle. So, for example, tilde S over D equals the absolute value of delta V over the absolute value of V. Now, watch what happens as we shrink theta down to 0. So, as theta approaches 0, tilde S is going to approach S, which at the limit equals ds, and delta V at the limit approaches dV, and so we have ds over d equals dV, absolute value of course, over absolute value of V. Now let's multiply both sides of this equation by the absolute value of the velocity. So this will go away, and on the left-hand side we'll have ds times absolute value of the velocity over d equal to simply the absolute value of dv. But now let's divide both sides by dt, and we can rewrite this as ds over dt times the velocity absolute value over d equals the acceleration, or dv dt. But look, ds dt is equal to the absolute value of the velocity vector. So what we wind up with is absolute value of the velocity squared over d equals dv dt. But we've already shown that dv dt is constant in a circular orbit, as is d, so v must also be a constant. Long story short, we have just shown that v squared divided by d equals the centripetal acceleration, which of course has to equal the quantity g times m divided by d squared, according to Newton's law. If some of this doesn't quite make sense, this would be a good time to pause the video and review what we just did, as shown here. So this is a very important finding, and notice that if we take this expression here and this expression here, and we multiply both by d and take the square root, we get the absolute value of the velocity equals the square root of gm over d. It turns out that this formula right here will be very useful to us later on when we consider non-circular orbits. Now we are ready to prove Kepler's third law for circular orbits. Let t equal the period of the orbit and let the absolute value of d equal the semi-major axis, that is, the radius of the circle. Then, logically, t must equal the area contained within a circular orbit divided by the rate at which the area is swept out by the planet. Well, of course, the area within a circle is pi times d squared, and the rate at which area is swept out by a planet is h over 2, as we have previously shown. And we have also just shown that h for a circular orbit is simply the absolute value of the velocity times the absolute value of d, and furthermore, that the absolute value of v equals the square root of the quantity g times m divided by the absolute value of d. And now we can do a little math magic. So let's say that this equals 2 pi d squared over h, or 2 pi d squared over square root of gm over d times d. And we can divide through by d over here. But now let's square both sides. So bring this over here, and we have t squared equals 4 pi squared d squared over g m over d. Well, we have to bring this, we can bring this d up here, and we get t squared equals 4 pi squared d cubed all over gm. So we have just shown not only that the square of the period is proportional to d cubed, but we have also shown that the constant of proportionality is 4 pi squared divided by g times m.